Okay, here's 3-2, day 2. And we're still really focusing on our least squares regression line. And we'll review a few topics we hit on day 1 and then dive into a couple new things. All on the same topic, though. We're going to start with continuing our discussion on the concept of a residual. Now this slide is asking about the car that had 70,000 miles. And I have calculated here that our line would predict it has an asking price of $12,704.40. Okay. Now the other residual we did in lesson 1 was right here. You might remember that one was negative 295.9, which told us that our line over-predicted the price by about $295. This one is a very different story. It's positive, and you can see from the scatter plot, that means our line gives us an under prediction. And we under predict by over $1,700. It's not horrible, but it's not great. It's a good one to do in addition to the other one because we saw that first residual, again, was relatively small and it was negative. This one is positive and it's quite large. And in fact, it's the biggest one on the scatter plot. But you can see that with the line I drew in. What that means is that point is the farthest one off the line. It's got the biggest difference between its actual asking price and the predicted one from our line. Okay, this is a scatter plot. It's called a residual plot. We have seen two pieces of data on it. Here and here. It's relatively simple. It's a scatter plot, and it compares two things. Like this point right here is 70, 1709.6. It takes every piece of data in terms of its x value, and the y value is its residual. This came from the first lesson. This would be the point 45, negative 295.9. Okay? The biggest thing that we're looking for, which the title obviously gives away, is we're checking for patterns. We shouldn't see any. Okay? If linear regression and a least squares regression line is a good way to model the data, we don't want to see any patterns. For example, okay, I mean really two things. No patterns, and again, the residuals should be small, right? Big residuals means the points are way off the line, which is that's not good. Really what we use this for is, you may recall that we looked at y equals x squared from 1 to 10. And we saw that r was 0.97. And like, hey, wait a minute, that's like really, really strong and linear. That's what r measures, but that's a quadratic, that's very not linear. What's the deal? This is what we would also look at, okay, where we'd have a little bit of kind of a chance to notice that is the residual plot for that data, that y equals x squared. It would show a really distinct pattern, okay? So if you see something like these two, where it's like, hey, the residuals are all negative, and then it switches up to positive, and then they come back down. And the same kind of thing here. That's not, I mean, it's evidence that your data, your original scatter plot, is nonlinear. Okay, so R pairs wonderfully with a residual plot. Oh, I might show you how to do this in the calculator. It's not something you'd have to do for a test, but you could on your homework. To calculate all the residuals at once, if you ever had to make a residual plot, I can show you how to do that. It's not terribly difficult. You just have to use your lists. I may not, I don't know if I'll make a tutorial to put on Schoology. I might. We'll see. It's certainly something I can show you in class. Two things with the residuals that we know from our regression line. Number one, if we just add them up, it'll add up to 0. This is just rounding error. And then number two, if you were to square all those, it would give you the least sum possible. That's why they call it the least squares. The square is referring to the residuals, the least squares regression line. All right, so we need to get into 2 new measurements, okay? One is called S. There can be a little bit of a point of confusion because you think of S as standard deviation, and it is, right? You wouldn't have to worry about being confused because this S only comes up if we're dealing with scatter plots and linear regression, right? We talk about our regular standard deviation if we had one variable and we were working on a normal curve. That's how it's calculated. You'll never calculate it. It's standard deviation. It should remind you a lot of the actual standard deviation formula. And here's its definition. Okay. Now, when we explain it, and I will show you exactly what I want if you were to explain it, that's not what we say. We don't say, oh, S is the standard deviation of the residuals. No. Okay. It tells us how much variability we get with residuals, but it actually goes right along with R squared. But let's get S first. S will tell us, and if you think about this, like if that the residuals are the points, like how far off they are. And S tells us how much variability there is. In context, S is going to tell us if we use our line to make a prediction, how far off we expect to be. Okay, which is a really good thing to know. It goes right along with R squared, which we've talked about R. So if we take R squared and multiply it by 100, that is the percent of variation in Y that's accounted for by our line. Okay? The reason these two things go together is because as R squared gets really big, S gets small. Okay? Both would do the same thing on the scatter plot. That if that's happening, if R squared is close to 100% and S is really small, it means all of your points on your scatter plot are really close to your line. Okay? As those points were to move away, R squared gets smaller, S gets bigger. Okay, let's look at an example here in context. All right, so we have R and S. The very first thing we should do is R squared is 0.86 times 0.86, or 0.74. Okay? Doesn't give us a least square regression line, but it'd probably look something like that. So comparing two variables, size of a diamond, measured in carats, and its price. Okay? It looks like the two are pretty potentially related. Like there's a strong association. I mean, we look at R and we're like, well, yeah, it's 0.86. Okay? So here are those two definitions we just saw. If you were to ask to interpret R squared in context, I would say 74% the variation in diamond price is accounted for by our regression line. And if you're asked to interpret R squared, your answer is going to look something like that. Okay? It's going to be something like that. The wording really shouldn't vary. Okay? 74% is a lot, right? These points are pretty close to the line, and what it's really saying is we feel like we could predict price from size pretty accurately. How accurately? Well, let's talk about S, which is 55.37. I would say when using our line to predict price, we'd expect to be off by an average of $55.37. Right? And it looks like we're trying to predict diamonds that are anywhere from like $200 some up to like $1,100. So it depends, but that's not that bad, right? R squared is pretty high. We feel like we can predict price pretty accurately. So as a result, S ends up being relatively low. Our predictions aren't off by that much. Again, look at the scatter plot. It makes sense, right? That's not the actual regression line I drew in, but it's probably pretty close, and those points are not that far off. All right, let's look at these ideas a little bit more. Okay, I want to take you through what I have here, because like on a test question, this is pretty close to what you would get. Okay. Oh, on the first scatter plot on the left, that is your scatter plot. Okay? Make sure you're good on your context. Sugar in teaspoons, I think that's teaspoons. That's what I'm going to call it. Is your X, and then flour freshness is your Y variable. Okay? Over here we have a residual plot. And down here we have output from a little computer program called Minitab. Okay? The end of your notes, I'll take you through kind of the parts of Minitab. Okay? Here's the things we may want. There's S. There's R squared. There's slope. And there's y-intercept. Everything else at this point in time, not interested. That's the only stuff I want, those four things. The equation is y hat equals 181.2 plus 15.2x x is sugar in teaspoons and y is freshness of the flower in hours. What's the slope tell us? It tells us for each additional teaspoon of sugar added, our line predicts freshness by about 15.2 hours. Okay. We can get R pretty easily because it does tell us R squared. And notice both of these are very, very high, right? There looks to be a very strong positive linear association between these two variables. Is a linear model appropriate? Okay, what I want to show you here is the kind of things to mention. Number one, yes. Number two, R is 0.93. Third, the scatter plot looks linear. And the residual plot shows no obvious patterns. And we'll wrap up with R squared and S. 86% of the variation in freshness is accounted for by our line. Again, you can think of that as like how accurately our line could predict y from x. If r squared were 100%, that means the points form a line. And s would be 0, because you could predict freshness perfectly from the amount of sugar. That's not quite the case. S, which is from Minitab, if you looked up there, if we use our line to make a prediction, we'd expect that we'd be off by about 7.5 hours. That's how much air we would expect. All right, general talking points. Nothing here that's super, super specific, or really anything to work through. But good things too. They're kind of like final notes about, hey, like these things came up, but these things are a big deal. Don't forget about them. Your explanatory and response variables are important. Okay. Make sure you set it up the way you want. This has two little scatter plots. If you switch x and y, s, r squared, all the numbers change. Okay, so that's important. Okay, don't lose sight of the fact that this whole R and this correlation stuff, it only describes linear relationships, right? So if we observe data that's nonlinear, we don't really have any tools to do much of anything right now. Okay? We looked at this with the standing mixer problem, particularly R, right? It is not resistant to outliers. Okay? It is very, very influential. If we mess around with one point on a scatter plot, the data can really change. That's a silly one, right? Instead, we mentioned it once, I'll mention it again. Stay firm. I don't care how strong the association is. We're not jumping to causation, right? If you're ever asked about it, any problem that hints, oh, do you think because of what we observed, this means that, you know, the x variable is causing the changes in y? No. Here's that summary of Minitab I was talking about. And that has everything marked kind of nice and neat, right? For now, be very clear. You're not into any of these other measurements. You just want those four.